Let me give you some intuition behind the concept of what it means to do a complex integral. Okay, so here we have e to the I theta. So assuming you're studying this subject, you should already know what e to the I theta is as a circle. Then what you do is you take some sample values of e to the I theta along the circle. Now remember, a complex number can be represented as an arrow. So that's pretty much what this shows. There are 20 of them, count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 arrows representing 20 complex numbers. The spacing between these numbers is always the same angle. We can call it d theta, whatever it happens to be. So that's the first part. Second part is the following. We take these arrows, which represent the different complex numbers, and we multiply them by d theta. That gives you a picture like this one. Now this picture, you should keep in mind, is a bit still exaggerated so that the arrows are visible. Otherwise, they're so small and clumped together, they're very hard to see. So I've zoomed in a little bit more. I've exaggerated them a little here. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to 20. There are 20 arrows. In other words, each of these arrows, like the first one here, you just multiply by d theta, which makes it smaller. And then you do that to each of the arrows here. That's why over here, you have the same 20 arrows. They're pointing in exactly the same direction. That hasn't changed. But because you've multiplied by d theta, each one has gotten smaller. At the last stage, this is what you do. You take these arrows and you add them together, tip to tip, just the way you add vectors, so look carefully. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 arrows added together. And because they've been scaled by this d theta, by this number, that it's made each one shorter, but it's kept their direction, when you add them together, you get this arc of blue arrows, basically. If you look very carefully at each individual arrow, it has exactly the same direction as the following. Going back to here. Look at the way this arrow points, the one that's a pi over 2 roughly. Look at the way it points. Now go over here and look at this one right here. It points still the same way. That's just its length is smaller and it's been moved to the tip of this one. Back here for a second. Take any intermediate arrow like this one that seems to be at about 45 degrees where I'm tracing. Go back to here. It's probably one of these arrows over here. It's 45 degrees, still the same direction, just its magnitude is smaller, the length is smaller. And then when you add all of them together, look at the complex number that you get from the process. Across the horizontal for the real part, it's 1 right here. And across this axis here, it's 1. So that means it's 1 plus I as the value of the sum. If you actually integrate from 0 to pi over 2, which is the angle. Now why is it the angle? One more time, look. Right, because these arrows here, they roughly begin at 0 degrees and they turn up to pi over 2 radians. So that's why over here they do the same thing. Like this one over here pretty much begins at 0 radians and then you come up to here. And this one is like pi over 2 radians. And then these arrows go through all the intermediate angles because that's what d theta means essentially. Alright, so then you get a nice arc. If you integrate, as I was saying, between 0 and pi over 2 e to the I theta d theta, you will get 1 plus I. But here, because I've used 20 arrows as our samples, you can see already that's a pretty close approximation that seems to be just about equal also to 1 on the horizontal for the real part and 1 on the vertical for the imaginary part. If you like, it was helpful.